All right. As the last stop in this section, let's see what happens when impulses are zero. So I have written here the principle of linear impulse and momentum again. Note that you can think of it either as the principle applied to a single particle or a system of particles. In this case, this velocity could represent velocity of center of mass, and you can study the entire system by just considering the single point at its center. So what happens when this is zero? The left hand side, if the external moment, why do I say moment? The external impulse acting on a particle or a system of particles is zero, that means mv2 equals mv1. And assuming that mass of the system doesn't change in that portion or in that period we are talking about, the velocity of the point remains the same. Or if it's a system of particle, the velocity of the center of mass of the system remains the same. An interesting example, maybe it is useful to mention here, is let's consider a projectile. Yeah, that's a good example. Assume it's New Year, you have fireworks, you have shoot up a firework thingy, I don't know what they're called, and somewhere here, all of a sudden it explodes, and you see all these little pieces coming out. What happens in this scenario is that you have a whole bunch of small particles inside inside that package of stuff. As this package explodes, in that relatively short amount of time, effectively all forces that are acting on these particles are all internal explosive forces that are pushing all the particles out. And let me see. Yes. And during that phase, you see everything essentially expands around the same point. So if all of these forces are internal and gravity is small and negligible compared to the rest of the forces, you expect that the velocity of center of mass does not change. And right at the top, the velocity of the center of mass, which is the pre-explosion velocity of the package, is relatively small, remains constant, or remains close to zero. And throughout the explosion, everything expands, but the center of that explosion remains more or less in the same location. One other interesting things happen, and that is you often see, as the time progresses, like a couple of seconds later, these ends of these explosions, they all start to come down like this, like a tree branches. All of them start to fall down, and if you continue track the position of all these particles, you will notice that the center of mass of all these particles is actually continuing with the same projectile motion. So the principle of linear impulse and momentum is actually being just tracking the projectile motion of the entire explosive package. Somewhere in the middle, all particles start to expand due to these internal forces, but the overall center of mass of the entire system continues to follow a projectile motion. Yes. So to come back out of this example, if the total external impulse on a system of particles is 0, the momentum of the center of mass does not change. That is the end result of the conservation of linear momentum. Linear momentum, yes. And you may wonder when that happens. It happens when it is useful, this principle, useful in many cases, whenever you have net external impulse, note that it is impulse that matters, force integrated over time. Whenever that impulse is 0 in any direction, you can assume the momentum remains conserved. And that often you can either approximate it or with confidence know that this external impulse is 0. One thing is, if applied external force is 0 as a vector or in any particular direction is 0, it means the momentum remains conserved. Another possibility is that force is not 0, but the integral is 0. So you have some forces, pushing the particle in this direction, and later the external forces reverse direction and start to cancel their initial function or initial effect. So when this integral of f dt, my emphasis is on integral, the summation over time is 0. Again, you can know that along that particular direction, the momentum remains conserved. Another important implication of this is that when you have a force that is not 0 itself, like force of gravity or force of a spring or an externally applied force, but when you take this integral, but your time, his time window, t1, t2, this time is very short. T2 minus T1 is very small. Again, although the value of the force is not 0, the very minute time window you're integrating leads to a very small and often negligible amount of impulse. So there are a lot of different scenarios that the principle can be applied, sometimes exact, sometimes with a very good approximation. And the example of fireworks is the last one, that during the very short time that you have this rapid expansion through explosive forces, because the time is small, you can assume the impulse is small, therefore the velocity of the center of mass remains the same. So that is what I wanted to say. Oh, one other important thing. Again, I emphasize external impulse matters. We do not need to care about internal forces. There are many cases that we cannot know how the internal forces work, but we can cleverly consider an outer boundary of the system and only see what happens from the outside. Knowing that information, we can go and start deducing what happens inside the system. But our entry point to the problem is that often the external impulse is zero. Okay, good. I think that is all I have. There isn't much else in this section. So we introduced the concept of linear impulse, the concept of linear momentum, how they are related to each other through the principle of linear impulse and momentum. We saw that for a system of particle, the principle applies, and long story short, you can only consider the motion of the center of mass of the system of particle in relation to all external impulses. And when the external impulse is zero, we can safely deduce that the momentum of the center of mass, or if the mass doesn't change, the velocity of the center of mass remains constant. And that is the conservation of linear momentum. So I stop here. In the next sections, we look at a particular use case of this framework of impulse and momentum. That is the topic of impulsive forces that are large but happen at a very short period, like contact forces or explosive forces and so on. And we expand this to the rotational domain. We look at everything but angular. So angular impulse, angular momentum, and the principle of angular impulse and momentum. Until then, I leave you with these concepts. I'll see you soon.